joining us online and via Zoom. And so we're going to start off with a talk from M.Matos. So welcome, Mariana. IBET in Portugal. So the question is it feasible to produce PHBV from various agri or food residues?
Thank you so much for the introduction. Can you hear me? Yeah. So, my name is M.Matos, as James said, and me together with my colleague Simone from Innoven.
The speakers stand around here, so this is perfect around here.
This is perfect. Okay.
Thank you.
So we're going to answer the question: is it feasible to produce PHBV from various agri-food feedstocks? So I will start with a short introduction about the topic for those who are not familiarized with it. Okay. And then I will show the first results achieved by IBET during the Glopack project. So polyhydroxyalkanoates, the PHAs, are a promising family of biopolymers, which are stored on the cytoplasm of many bacteria. And they are thermoplastic, which means they can be processed as the classic plastics, but they have a big advantage. They are bio-based and fully biodegradable in both aerobic and anaerobic conditions. So the PHAs are very versatile. They can be more flexible or rigid, depending on the monomeric composition. And they are also water insoluble and resistant to fats and oils and have a very low oxygen permeability, which are all good characteristics to be used as a packaging material. So in specific, the PHBV is a copolymer of HB and HV monomers, and they have improved mechanical and thermal properties in comparison with the homopolymer PHB, which is the most studied PHA. And it is important to overcome the technical obstacles associated to the PHBV production, turn the actual linear plastic chain into a sustainable cycle. The commercial PHAs are currently produced using pure cultures, and they are fed with high purity substrates. So in this type of process, there are a need of sterility and restrict control, which means they are high energy demand processes. And the cultures are usually fed with pure glucose or corn skip liquor, which are pure feedstocks, and they account for almost 50% of the total production costs. So this makes the PHA that have a very high price to be used as a commodity material. Over the past 20 years, an alternative process based on the usage of mixed microbial cultures and residues has been developed. So I can tell you straight away that it is possible to produce PHBV from various agri-food feedstocks. And this process usually comprises 3 steps. We have an acidogenic reactor here, where the organic carbon of the feedstock is converted into a mixture of soluble fermentation products, which are PHA bioprecursors. And then we have 2 aerobic reactors. The first one where a mixed microbial culture is selected based on the PHA storage ability through inducing periods of feast and famine. And then we have the PHA production, where this culture is inoculated and the culture is fed with the soluble fermentation products produced here in the cytogenic reactor until they achieve their maximum PHA capacity. Then the PHA is down processed, which means it is extracted, purified, and dried, and we obtain a pure PHA at the end. During the Glopack project, the IBET was on charge of optimizing the PHA production efficiency, and to produce 50 kilos of PHBV. We were mostly working on the work package 2 of the project, and we used fruit waste as feedstock. This feedstock is globally produced in large volumes. It accounts for up to 60% of the fruit production. And in our case, it was supplied by a Portuguese fruit and vegetable process company. And it is obtained from the store barrels that do not comply with the criteria to be processed. This feedstock has a high total carbon, organic carbon content, which means it is easily biodegradable, which increases the potential to be converted in soluble fermentation products and, of course, in PHBV. So here you can see our pilot plant. We have 3 reactors to perform the 3 steps of the process. We are currently at the TRL between 5 and 6. And we operated the first reactor, the fermentation reactor. It is a 60-liter flow anaerobic sludge glycol reactor. And we operated it at 30 degrees, and we adjusted the pH, trying to control the PHBV composition, which means the HV monomeric composition of the PHBV. Then we have a selection reactor, which is a 100 liter sequential batch reactor. This reactor was operated at room temperature, and we adjusted some operational parameters as the sludge retention time and the organic loading rate of the reactor, trying to optimize the efficiency of the culture. And then we had the final reactor, which was a 60-liter fed batch reactor inoculated with 25 liters of inoculum from this reactor. And it was operated at room temperature, and the culture was pulse-wise fed. So the first research work that we did during the Glopack project was to understand if it is possible to control the PHBV monomeric composition with one single system and using the same feedstock. So to do that, we operated the first reactor under dynamic pH, trying to change the soluble fermentation products produced. So we tested 4 pH values. And as you can see in this graphic, the fermentation yield was quite stable. So the process is efficient in terms of yield for all the pHs. But the soluble fermentation product composition highly varied with the pH. We saw that the HV bioprecursors, which are propionate and valerate, linearly increased with the pH here from 4.79 until 4.92, which will possible reflect in the polymer composition. Then we tested each one of these streams in the production reactor. So we fed the culture with those streams. And we saw that actually the PHBV monomeric composition can be manipulated by the pH of the waste reactor. You can see here that the HV monomeric composition of the polymer varied between 16 and 44%. So it was possible to produce different polymers with different properties, which means for different applications, using one single feedstock and one single system. Then we tried to control the sludge retention time and the organic loading rate of the selection reactor, this reactor here. So we operated 2 SVRs with 2 sludge retention times, 4 days and 2 days, and we 4-step increased the organic loading rate until a maximum of 14.5 grams of COD per liter per day. We saw that the biomass productivity was similar for both reactors, for each organic loading rate, but the culture selected at 4 days of SRT had a higher PHA accumulation capacity. So this reflected on the global productivity, which was 80% above of that achieved for the 2 days of SRT. So we saw that either SRTs favored the global process performance. We also did a mass balance considering the production of 1 kilo of PHBV with 19% of HV monomers, and we considered the individual reactors results achieved during the PHA production for the Glopack project. And we saw that 1 kilo of PHBV can be produced from 67 liters of fruit waste, which is a result that is in line with the literature results. We, during the pallet plant operation, we faced off with some roadblocks. We tried to have a solution for each one of them. First, we saw that the feedstock had a high solids content. So we had to install a decanting system in continuous mode to filtrate the feedstock after the acidogenic fermentation and to have better results in terms of purity of the polymer. Then we saw that the feedstock varies along operation because it is a waste, so it is normal. But the culture was very well selected and adapted well to the variability of the feedstock. We had some problems in the extraction process, which was done by another company. Those problems were mostly related to the variation of the culture along operation to give a response to the feedstock variability. And they also saw excess of foaming and heating at certain point of the extraction. So we had to tightly control the PHA content on biomass and to adapt the extraction method and to do the extraction in smaller batches. Then we saw that sometimes there are a high level of impurities on the polymer. So we installed the second round of purification. In sum, we were able to continuously operating the pilot plant during several months continuously, and we achieved overall good key performance parameters. We produced an average value of 4.9 kilos of PHBV per month, and we saw that it was possible to produce PHBV with different monomeric compositions. On total, we produced 72 kilos of PHBV from fruit waste, and we delivered to partners 31 kilos after extraction. The polymer had a good average molecular weight, and we sent polymers with 2 HV grades, 18% and 30%. For the future, we think that it is important to optimize some operational conditions factors and to analyze the possibility of recycling processed wastewater to decrease the tap water consumption, to study online monitoring techniques for better process control, to develop predictive models for process optimization and to design large-scale plants, and of course to demonstrate the PHBV production from different organic residues at a larger scale. Now we're going to do the transition for my colleague.
That's right.
Simone.
That's right. Thank you very much, Mario. Thank you very much. We're going to pass straight on now to Simone Nortilli.
Yeah. Good morning.
Simone.
Good morning. Can you hear me? First of all.
Yes. Yes, we can hear you. Thank you.
Okay, perfect. Do you want just to share my screen, or how do you want to proceed?
No, we don't need to do that. You can just say next, please.
Okay, so next, please.
Yes.
Perfect. Okay, so thank you for the introduction. First of all, good morning to everyone. I'm Simone Nortilli. I'm going to talk about the Innoven role inside the Glopack project and especially the PHA production at pilot scale. As Mariana explained you before, together we were in the task 2.1, so in the PHA production, but the main difference was the use of the feedstock, which was made by agricultural residues, and especially corn cob. Next, please, James. As you can see, just to have the overview of the plant for the operational condition, we were inside an agricultural society very close to Verona, inside which there were 2 full-scale anaerobic digestion plants, and we were fed daily by this company for our activities. Next, please, James. This is just to make you understand how we proceed, the general overview of our pilot plant scale. So starting from the early stage, you could see that the material was fed inside this external storage tank and successfully grinding and pumping before to be charged inside the stage 3, in which we obtain defermentation for the volatile fatty acid production. Which it is an important step for the mixed microbial culture and PHA production. Then we had to separate this fermentative product by the use of a screw press and divide it, so the solid fraction from the liquid one containing our volatile fatty acids. Just to show you that the current state of this development and the pilot plant count in terms of TRL is between fifth and sixth. Please, the next one, James. No, one before. The one before, okay, perfect. Then once we recover the volatile fatty acids, this has to go inside the 2 stages 6 and 7, in which we first select the biomass able to store the PHA, and then we accumulate. So we actually produce the PHA that you can see in stage 8 and 9, in which we try to fix the biomass, so concentrate the biomass as much as we could, and then ready for the downstream process, so for the extraction and purification that you will see later. Next one, please. So in terms of result achieved, this is the fermentation unit, a big fermentation unit from the volume of around 4 meter cubic for the production of VFA. The operative condition that we adopted were HRT of 4 days, always conducted in anaerobic condition in a mesophilic temperature, so between 35 and 37 degrees, with an organic loading rate of around 18 kilograms COD per meter cubic. Next one, please. In terms of volatile fatty acid production, this is the overall production that we kept in grams O2 per liters, which is around 10, and as main product acetic acid, followed by propionic acid and the other long chain volatile fatty acids. Next one, please. After we obtain the fermentative product, this has to be filtered in order to have a proper selection and accumulation process. And we faced here the first problems related to this material. As you could see, in fact, the classification of the total solids in the liquid fraction was still high, even though we try to filter using the serial filter you could see from the picture. And a lot of total suspended solids and inert material. So, for instance, presence of fibers, salts, and probably lignin coming from the agricultural residues were still present inside this liquid, and we were trying to solve this problem. Next one, please. So we decided to adopt another kind of filtration machinery, which is based by two stages of separation and by different layers of mesh to be used to try to achieve this problem. As you could see, there are many layers starting from, in the first stage, 200 micrometers to 50 micrometers, and in the second one, from 100 micrometers to 50 micrometers. Next one, please. We try to adopt this system, but it wasn't significantly efficient, let's say this, because in terms of variation of total solids and total suspended solids, we decrease it a little bit, but not completely. And in terms of distribution of solid and liquid phase, we could have seen that the volume of the permeate recovered was best achieved by using as first stage layer 100 micrometers and second stage layer 50 micrometers. So further analysis on advanced technology filtration system has to be developed. Next one, please. Yeah, this one is the selection process. As explained before, Mariana, I don't want to focus the attention too much on this because the system on the mixed microbial culture is more or less the same. We change, of course, the parameter used for the selection of this biomass. Especially, yeah, we could say that we kept an HRT equal to SRT for 2 days, and as organic loading rate 2 kilograms COD meter cubic per day at a temperature kept constant at 25 degrees with the following ratio in terms of nutrients that you could see from the table. In terms of volume, it's a big selection batch reactor because, as you could see, it was around 2 meter cubic of reactor. Next one, please. And this one is the following step of the process, so the accumulation SBR. Even in this case, the biomass in terms of grams per liter were approximately 1.6 grams per liter at the starting of this step, and we fed this reactor by a spike of VFA consistently in 0.5 grams per liter per addition, and we achieved the let's say best condition and accumulation by the add of 5 of this spike. Next one, please. Okay, we arrived at the end of the process of biomass enriched PHA, and at the end of the accumulation step, we had to recover the biomass and first stop the microbial activity by reaching a PHA of 4, and then try to concentrate the biomass and separate that from the water and S.Nortilli still present inside the reactor by using a polyelectrolyte and taking again the biomass to pH 2. Next slide, please. So we brought our biomass inside the lab, and from the picture on the left, you could see that we use a rotating ceramic membrane, which contain a filter by able to separate the biomass at 0.22 micrometers. But it had a low flow rate, so we took a lot of time to concentrate this biomass ready for the extraction and purification that needs to be done to extract the final product. In terms of extraction, we perform it by using a solution of hypochlorite for the digestion. We used many solutions, but then we use the one at 5% of concentration of it. Then centrifuge this biomass to separate again the water and trying to concentrate and remove the impurities that you could see from the picture were still present due to the presence of the fibers and other impurities in the VFAs, and then try to wash as much as we could this biomass to obtain the extracted PHA. Next one, please. once we got this final extracted PHA wet, we had to perform the drying step, and we perform it for around 60 degrees overnight in order to, of course, obtain the powder, the final powder, to be delivered to our partners. Next one, please. Yes, this one is slides from the biomass extraction purification, just to summarize in terms of balance how much grams of PHBV could be obtained, starting from around 1 kilograms per batch of total volatile solids of biomass, plus the extraction performed in hypochlorite, and plus the wash methanol and water solution. We obtain a recovery yield of around 70–80% with content of PHBV on the biomass of around 30%. So it means 300 grams produced per batch with an HV content of around 10–15%. Next one, please. We encountered three, let's say, big issues during these experimentations. In the first case, of course, the high level of polymer impurities that we could try to solve adding washing steps with water and methanol, and trying different combination of solvents to remove these impurities. Still presence of inert materials and solids, as you could see in the VFA streams, could be solved by the use of advanced mechanical or physical chemical filtration. And in terms of biomass enriched PHA recovery, just to solve the problems of the flow rate of the rotating ceramic membrane, we think that it could be adopted as sedimentation at the end of the accumulation step, or a centrifugation step directly in the plant to make it faster. Next one, please. So just to answer to the initial question on the presentation, is it feasible to produce PHBV from various agri-food residues? Yes, it is feasible, but of course, part of the process is still have to be optimized. In fact, the pilot plant has been modified from the initial state by us to improve the PHA production. We reached around a production of 10 kilograms of biopolymer, but of course, due to the difficulties encountered in separating the inert materials from the fermentative product and the difficulties encountered in set up a proper extraction and purification protocol, it is possible, of course, to produce PHA with HV, so valerate content around 10–15%. We obtain a fermentation yield in line with the literature data, and it is possible to obtain a yield of around 6 kilograms of PHA per ton of corn cob wet weight, but of course with the improvements required in both clarification of VFA stream and extraction purification protocol. Next one, please, which should be the last one. Yes. So future prospects in terms of optimize the operational condition of the plant. So for example, the separation of the VFA stream. For us, it would be nice to introduce new separation technologies with higher efficiency, like nanofiltration, ultrafiltration, or reverse of osmosis, and deeply optimize the extraction and purification protocol by investigating the different use of solvents to improve the recovery yield. And of course, for the future, optimize at best the production of the PHA at pilot scale, which, as you could see from the picture shown, our is very, very big, perhaps very close to a demonstrative scale in terms of volumes treated. Thank you.